to talk about stochastic dual coordinate ascent for learning sign constraint in predictors. In the study, we will consider linear classifiers. As an example, we will consider the case where the feature vectors are from x1 to x4 and the weights are from w1 to w4. Since this in a product of w and x equals to 0.28 in positive, we predict as positive. Similarly, if we have features in weights like this, then we predict it as negative. And presented with the feature vectors as a bar graphs and the weights as line graphs. It looks like this. You can see different weights produce different predictions. The ideal weight is the one that minimizes prediction error. The weight is determined from the training data. Let's assume that the positive samples are given like this, red cross mark. Following that, let's assume that the negative samples are given like this, blue cross mark. Changing weight that will alter the prediction scores for each of the training data. If we know the true distribution, we can calculate the generalization error or error rate and predicting with that weight. The ideal scenario is to determine the weight in such a manner that the generalization error is minimized to the greatest extent possible. However, the reality we face is that the true distribution is often unknown, making it possible to calculate the generalization error or to determine the optimal weight. In practice, the determination of the weight is achieved by minimizing the upper bound of the error rate, denoted as P of W, using only the training data. This is referred to as empirical risk minimization. The availability of substantial amount of training data opens up the possibility of reducing the error rate for unknown data. However, we often encounter situations where the number of training data is limited. Therefore, we have devised a method to compensate for the scarcity of training data by leveraging domain knowledge. To be more specific, we represent domain knowledge using a constraint called a sign constraint. An application called microbiological water quality prediction served as the motivation for this research. In microbiological water quality prediction, the domain knowledge refers to the relationship between the features and class labels. A relationship that understood between the features and class labels are utilized in this domain. We improve the predictive performance using domain knowledge. In microbiological water quality prediction, it is known that there is a positive correlation between the above 4 features and the number of coliform bacteria. It is also known that there's a negative correlation between the remaining features and the number of coliform bacteria. This domain knowledge is utilized in machine learning. As I mentioned, domain knowledge is represented using a sign constraint. Let's consider an example of such an optimization problem. In this case, imposing constraints such that variable W4 is greater than or equal to 0. If the fourth feature has a positive correlation with the class label, it can be expected that the generalization error will be minimized. The left side represents when a sign constraint is used, while the right side represents when it's not used. By introducing the sign constraint that represent domain knowledge, predictive performance can be improved. In summary, traditional machine learning simply minimize P of W without any constraint. Let's denote the set that satisfies the sign constraint as S. In the context of optimization, the set S is so-called feasible region. The proposed method optimizes the weights only within the feasible region S. So let's start by revisiting the learning method of typical binary classifiers such as support vector machine. Suppose we have these 5 red points representing positive examples and these 5 blue points representing negative examples. We will consider a machine learning problem that determine a linear decision boundary based on these examples. In support vector machines, we construct a linear decision boundary. The phi area is referred to as a margin. On the boundary, the prediction score, which is the inner product of the model parameter W and the feature X, is 0. At the edge of the margin on the positive sample side, the prediction score is +1. And then at the edge of the margin on the negative sample side, the prediction score is -1. For the learning method, the support vector machine is often described as training so that examples are unlikely as possible to enter the margin. It can generally be viewed as a searching for W that minimizes what is called the legalized empirical risk. Not only support vector machines, but also logistic regression learned by minimizing the legalized empirical risk. Taking support vector machines as an example, let me explain what legalized empirical risk is. Let's represent the normal to the boundary surface with such line. The prediction score of each example will be the projection onto the normal of this discriminant surface. By projecting onto the normal line, we can determine the prediction score and thus calculate the loss each example experiences. In SVM, the loss is used represented by the red and the blue lines. A non-zero loss occurs when the positive example has a prediction score less than 1, and similarly, a non-zero loss occurs for a negative example with a prediction score greater than -1. The concept of the legalized empirical risk is derived from these losses. The second term represents the average of these losses, also known as the empirical risk, while the first term is a legalization term. In simpler terms, the combination of the legalization term and the empirical risk is what we call the legalized empirical risk P of W. In the case of support vector machine, our goal is to find the value of W that minimizes legalized empirical risk P of W. In the context of logistic regression, the binary closed entropy loss function is adopted as a loss function. And various other loss functions have also been used. For example, binary closed entropy loss, square error loss, quadratic hinge loss, smooth hinge loss, and so on. All of them are smooth and convex functions. In this study, we assume a smooth and convex loss function. In this study, we adopted an optimization algorithm called SDCA to find the W that minimizes the upper bound of the generalization error P of W. In addition, the SDG, namely the stochastic gradient descent method, can also be used. But SDG tries to minimize P of W directly. Instead of minimizing P of W directly, SDCA maximizes its Fenchel dual D of alpha. The advantages of SDCA are that it has a clear stopping condition. It does not require hyperparameters like step size. When SDCA is run, the difference between P of W and D of alpha converges to 0. Thus, the iterations of SDCA can be stopped once it falls below a certain level. SDCA is updated the Fenchel dual D of alpha for each dimension. For example, considering for examples, the dimension of the variable alpha is 4, since its dimension is the number of examples. This panel plots the Fenchel dual D of alpha against alpha 1 with the remaining dual variables alpha 2, alpha 3, and alpha 4 fixed. The panel below is an enlarged view of this panel. Ideally, we update alpha 1 to the position where D of alpha is maximized. This panel plots the Fenchel dual D of alpha against alpha 2 with the remaining dual variables alpha 1, alpha 3, alpha 4 fixed. The panel below is an enlarged view of this panel. Ideally, we update alpha 2 to the position where D of alpha is maximized. This panel plots the differential dual d of alpha against alpha 3 with the remaining dual variables alpha 1, alpha 2, alpha 4 fixed. This panel plots the differential dual d of alpha against alpha 4 with the remaining dual variable alpha 1, alpha 2, alpha 3 fixed. Ideally, we update alpha 4 to the position where d of alpha is maximized. However, there exists no closed form solution to this maximization sum problem in general. The differential dual d of alpha can be expanded in this way. The update amount delta alpha being an argument in the loss function makes it difficult to maximize in closed form. For example, the update rule representing alpha 1 at which d of alpha is maximized cannot be expressed in closed form. Instead, SDCA maximizes the lower bound by updating the dual variables. When the loss function is assumed to be smooth, it becomes more manageable in the expression for the lower bound. The update amount delta alpha can be separated from the arguments of the loss function, simplifying the mathematical handling. Even if the lower bound is maximized at each iteration, the linear convergence to the optimum is ensured. But how should we maximize this lower bound? To find the maximum value of the lower bound, we consider three cases. The first case is when the gradient is 0 or less at it is equal to 0. The third case is when the gradient is 0 or greater at eta is equal to 1. The second case is when neither of the previous situation applies. In this case, there exists an eta such that nebula J super T as a 1, eta is equal to 0. It is necessary to find such an eta. So we discovered that the lower bound is piecewise quadratic function. In the next few slides, you can see the information. This is a slide explanation about the lower bound. I skip the detailed mathematical deliberations, but the lower bound is G super 1 sub T, can be expressed in A sub K eta squared plus B sub K eta for any interval flow theta K to theta sub K plus 1. This implies a lower bound quadratic function. From this fact, we can construct implementation with order of D squared. The heaviest step in this implementation is the step computing in the sets HK step 5 and the step computing coefficients A sub K, B sub K. Step 6, both which of pays order D squared cost. The overall, one iteration of SDCA can be constructed at the computational cost of order D squared. Furthermore, upon careful analysis, it was also revealed that one iteration of SDCA can be constructed at the computational cost of order of T log D. This is order of T log D implementation. Specifically, by configuring this way, we can find a dual variable that maximizes the lower bound at the computational cost of order D log D. So that's all I have to say about the method we used. Based on what we discussed so far, we conducted pattern recognition experiment to confirm the effect of the sign constraint. Next, I'm going to talk about the results. We conducted a numerical experiment as follows. The dataset used a subpolar, Indian, NMI top, and NMI bottom, totaling 4 in the number. The loss functions, multi-hinge, quadratic hinge, and binary cross entropy were used for comparison. For each loss function, the conventional learning and the sign constraint learning were performed. On this slide, you can see 4 plots, each representing the accuracy in their respective datasets. In the top left, we have the result for subpolar. The top right showcases the result for Indian. The bottom left features a result for NY top, and in the bottom right, we have the result for NY bottom. The horizontal axis represents the number of training data. The solid curves indicate the accuracies of predictors optimized under sign constraint. And the dashed curves are the accuracy when the sign constraints are not employed. It is noteworthy that the predicted performance has improved with the use of sign constraint in respect of the loss function employed. From these results, we have been able to verify the prediction made through sign constraint are indeed effective. We also measured runtime. I show you the next slide. The red solid line shows the order of the Ruby algorithm, while the blue dotted line represents order D squared algorithm. Surprisingly, order D squared algorithm exhibits faster performance, which may seem counterintuitive. This unexpected result might be attributed to the fact that we use MATLAB for implementation. However, it's important to consider that there could be other contributing factors. We acknowledge these possibilities. The limits are addressed in as a part of our future challenges. I summarize the main points. Sign constraints were introduced to learn linear predictors. SDCA was developed for empirical risk minimization. We found that each SDCA iteration can be within linear runtime. We demonstrated sign constraint in the application to the microbiological water quality prediction. That's all. Thank you for listening.
And